So the title of my talk is Floer Homology with DG coefficients. DG meaning differential graded, applications to cotangent bundles, and everything that I will talk about today is joint work with Jean-François Barraud, Mihai, Damian, and Vincent Humilière. So, and everything that I'm gonna talk about is contained in two preprints that we have on the archive. So, since it's supposed to be a talk accessible to a broader audience, I'll start with a broad motivation, mentioning the fact that a fruitful line of investigation to detect symplectic phenomena is to compare classical invariants coming from differential topology or algebraic topology to their quantum counterparts, meaning that they involve holomorphic curves. So the comparison, there's a little scheme that I drew here. The comparison happens on this side. And there's the quantum invariant, which may differ or not from the classical invariant. And in turn, the quantum invariant...
Alex, I don't see your iPad.
Yes?
I don't see your iPad. I don't know if anyone sees the iPad, but I
was going to say, yeah, I do see it.
I see. Okay, sorry. It's my fault. Sorry.
It's fine. Yeah, so I was saying that we compare the quantum invariant with a classical invariant, but the quantum invariant has several incarnations typically in the shape of Floer homology, which is filtered and gives rise to spectral invariance. So there's actually two comparisons on this side, but also on this side. So here's examples, like quantum homology, which has implications to the Arnold conjecture, or for example, to quasimorphisms. Yeah. Most recently, quantum Steenrod squares. Yeah. When they differ or they do not differ from the classical Steenrod squares, they have implications to understanding pseudo rotations. The invariant that I will use today is symplectic homology, which has applications to the Weinstein conjecture and the existence of periodic orbits on given energy levels. And I'll give a specific example about how the proof of the Weinstein conjecture in R2N goes using symplectic homology. So this is a celebrated foundational result of Claude 87, saying that whenever we have a closed hypersurface in R2N, which is of contact type, we find at least one closed characteristic on that hypersurface. So I will explain the terms. A closed characteristic is a closed integral curve of the line distribution determined by the kernel of the restriction of omega to the hypersurface. In a different incarnation, if we think of the hypersurface as being an energy level set, yeah, meaning a regular level of a Hamiltonian, then this is a closed orbit of the Hamiltonian system on that energy level set. Yeah? So what does contact type mean? It means that we have locally near the hypersurface a Liouville vector field, meaning a symplectically conformal vector field that's also transverse to the hypersurface. This assumption actually implies the fact that the whole neighborhood of the hypersurface is foliated by hypersurfaces on which the dynamics is conjugated to the one on sigma itself. So from the perspective of symplectic homology, the proof that I will present is actually I learned from Claude's GAFA 99 paper, and proceeds from comparing the classical invariant given by singular homology with the quantum invariant that's symplectic homology. Yeah. So what's symplectic homology? Apart from looking at, say, if I have a domain here that's enclosed by the hypersurface sigma, apart from looking at the topology of the domain, we also complement it by dynamics on the boundary. So it counts not only the topology inside, but also periodic orbits of Hamiltonian system on the boundary. So as such, there's a canonical map that goes from the interior of the domain to the symplectic homology. And let's compare. On the one hand, we can enclose a hypersurface in a big ball. So we have something that we understand very well, namely the symplectic homology of the ball. It happens to vanish. And the homology of the ball itself, which is non-zero. And on the other hand, the map induced in cohomology from the ball to the interior of the hypersurface certainly is injective because the ball has homology supported only in a single degree. So we find here a class, right, that is killed in symplectic homology and then further here. On the other hand, its image in the classical part of the interior of our domain is non-zero and necessarily gets killed by what? Well, by a periodical. So when applicable, this method produces contractible closed characteristics. So what about cotangent bundles? So I'm looking at a smooth closed manifold. I'm looking at its cotangent bundle, which carries the canonical symplectic form. And again, a foundational result of Helmut and Claude, perhaps 89 or around those years, saying that if we have a closed hypersurface inside the cotangent bundle that has contact type and such that it encloses the zero section, then it carries at least one closed characteristic. So there's this assumption on enclosing the zero section. Not everybody, but still very good. So how would the previous scheme function? Well, it does not. And as a matter of fact, it cannot as such, because as I noticed earlier, it would produce contractible closed characteristics. And it is not true that, say, on the boundary of the unit disk bundle, I always have a contractible closed characteristic, if only because if I look at the boundary of the unit disk bundle for a Riemannian metric, those correspond to closed geodesics on the base. And there are manifolds that do not admit contractible closed geodesics. So what goes wrong? Again, we look at the same picture. We have something that we understand well, namely symplectic homology of the unit disk bundle. This, by a theorem of Claude, is the homology of the free loop space. On the other hand, the classical part now is the homology of the constant loops. Yeah? First problem, this map is always injective. Yeah? And then we have the restriction map going from the homology of the unit disk bundle to the homology of the interior of the domain that we want to consider. So the previous scheme doesn't function because this map is injective, and therefore I have no control on how to find classes here that would be killed inside the symplectic homology of the domain. Can we make this map? There's a little delay, like I'm drawing on my iPad, but there's a little delay. Can we make this map from the homology of the constant loops to symplectic homology injective? Or it is injective, sorry. Can we make it non-injective? Can we make, as I wrote in red on the bottom of this page, the symplectic homology, meaning the homology of the free loop space, smaller than the homology of the constant loops? And our answer is yes, using this new notion of differential graded coefficient. So I will state the general criterion for almost existence, yeah? Meaning existence on almost every energy level near an arbitrary hypersurface of a contractible closed characteristic. Namely, if I pick a domain with smooth boundary, and the smooth boundary of this domain U is my desired energy hypersurface inside the Liouville domain, think cotangent bundle. And if I find a class in the classical part, which goes to zero in the symplectic homology, but which stays non-zero when restricted to the domain, then I have almost existence. Almost every energy level near sigma carries a contractible closed characteristic. Yeah. And this almost existence notion goes back to Hofer and Zhou. So that's the general criterion. And the point is that we have to understand, and you have to understand, and this is the message I want to convey, this criterion as functioning not only with constant coefficients, it's not necessarily with z coefficients or with field coefficients. These homological objects are going to be computed with fancy coefficients. So here's a few statements that we prove. Yeah. This is the first. So everything is going to happen in the cotangent bundle. I take a closed orientable manifold. And now I place myself in the following situation. I take a closed, some different closed and manifold and a map that sends it inside the cotangent bundle. And I will look at hypersurfaces that enclose the image of such a map. Yeah. This is the condition that I wrote on the bottom. Let me denote D, the degree of the composition projection composed with this map. So I have a map from my reference hypersurface, reference n manifold to Q. And then we have two assumptions, two distinct assumptions. Either we assume that Q is not a k pi 1, and the degree is plus minus 1, or we assume that Q is not a rational k pi 1, and the degree is non-zero. And in both of these situations, we infer the fact that almost existence holds for any hypersurface that encloses the image of such a map. So k pi 1 means that all higher homotopy groups are 0. This is what I wrote in red on the side. So not being a k pi 1 means that I have some higher homotopy. Being a rational k pi 1 means that all higher homotopy groups are torsion. Yeah. Not being a rational k pi 1 means the contrary. So one situation to which such a theorem applies is, for example, if S is an embedded closed exact Lagrangian submanifold. Yeah? We know that the projection is a homotopy equivalence. It has degree 1. And so any hypersurface that's going to enclose one such is going to carry closed characteristics. Here's another statement which does not make use of any such artificial manifold coming from nowhere. Yeah. We assume that Q is not a rational k pi 1. As soon as the projection map from the interior of sigma to the 0 section induces a non-zero map in n-dimensional homology, we have almost existence. The way this statement, so in my talk, in the last part, I will explain the proof of theorem 1 in the case where the degree is plus or minus 1. So for theorem 2 follows from theorem 1 because we can represent homology classes up to multiply with rational coefficients. We can represent them by submanifolds, or at least by maps coming from submanifolds. So it goes via such an application of results of Thom. Here's a corollary. again, about exact magnetic cotangent bundles. We take Q again, closed orientable, and we perturb the canonical symplectic form on the cotangent bundle by pulling back an exact 2 form on the base. So certainly the previous statements will hold for this so-called exact magnetic symplectic form. And in particular, for any exact symplectic magnetic form, on any hypersurface that contains the zero section, we have closed characteristics, as soon as the manifold is not a K-pi-1. So I've written on several slides various references to the literature. So here in the exact, there's a incredible literature on magnetic cotangent bundles. So such a result actually generalizes or complements things that were proved by Contreras, Maccarini, Paternain, Benedetti, Ritter, Groman, Mary. So these are the results, and we can take a small break so that you can ask questions if you have any before I go to explaining the construction of Morse homology with differential graded coefficients. If there's any question.
Is there like a slogan like we can keep in mind for why having graded coefficients helps? Is it the grading or is it the differential structure, first of all, that helps?
Oh, the coefficients are not going, the coefficients are going to be, I'm going to explain what I mean by that. And they're going to be chain complexes with extra structure.
Mm-hmm.
Yeah.
Okay.
So the definition comes right away.
Okay. Then I'll hold till then.
Any other question?
Yeah, Alex, just a question. So you have almost existence, but assuming you add structure like products or things, or maybe even again changing coefficient, can you infer more than one orbit in the existence?
For the time being, nope, because we haven't constructed the product structure in this setup.
Okay.
And there's yeah. For the time being, we're just using the fact, we're just using the objects at additive level. In principle, whenever one will have product structure, there's going to be also multiplicity results. But that's not constructed yet.
Okay.
Okay. I'll continue and go to explain. Actually, this I should have written here Morse homology rather than Floer. Yeah. And this is Morse homology with DG coefficients. And motivation number 2. So whatever I will talk about revisits and reinterprets a construction of Jean-François Barraud and Barraud-Cornea in 2007. They call it enriched Floer complex. And on a personal note, I was always fascinated by that construction. So somehow I would constantly go back to it and have the impression that I didn't really understand what was going on there. And finally, after all this work that we did with Jean-François and Vincent and Mihai, I feel I understand it better. So that was my personal motivation number 2. And the setup is the following. So let's start with a path-connected topological space. With a base point, I consider Moore-based loops. These are going to play a key role in everything I'm going to say. So it's based loops, so the loops that start and end at the base point, which are parameterized not by 0, 1, but rather by an interval of arbitrary length. And the advantage of such a parameterization is that concatenation is now strictly associative. Because upon concatenation, the length of the intervals just get added. And the outcome of that is that on the chains on the Moore base loops, and I will not pronounce Moore anymore, the chains on the base loops, we have a strictly associative differential graded algebra structure. Yeah. And I will also use cubical chains. They are easier to work with than singular chains when we speak about products. So this is a DGA. And by definition, a differential graded local system, and sometimes called derived local system, sometimes called infinity local system, is a right module over chains on the base loops. That's my definition. So it's a chain complex that has a right module structure over the DGA of chains on the base loops. And I'm now giving you the main source of such differential graded local systems. These are fibrations. So if I start with a Hurewicz vibration, it is known by work of Hurewicz, Fadel, Guggenheim, Dyer-Kahn, which happened at the end of the 50s and in the 60s, that it admits a so-called transitive lifting function, which is unique up to homotopy and up to replacing the vibration with a naturally equivalent one, fiber-wise homotopy equivalent. Yeah. So what's this transitive lifting function? I can phrase it as exactly what I want, and that's what I'm going to do. So topological module structure on the fiber over the base loops. Yeah. But the way one has to think of this is as holonomial. Yeah. So a lifting function arises from the following thing. Like, how does a loop on the base, sorry, what am I doing here? Oops. How does a loop on the base, the gamma that I drew here, act on the fiber? Well, it takes a point, A, and associates to it another point, A times gamma. And one has to think of that as being the end point of a lift of that loop to the total space. Yeah. So actually, Hurewicz was giving the definition of vibration exactly in these terms. Yeah. And existence of such lifting functions, so compatible ways of lifting all loops on the base to paths, or all paths on the base to paths in the fiber, is actually equivalent to the homotopy lifting property with respect to all spaces. So this is analogous to what the deck transformations do for covering spaces. And again, for those of you who are more geometrically minded, like if, for example, I have a smooth finite dimensional vibration over a manifold X, yeah, any choice of connection, meaning at each point a plane that's transverse to the fiber, right? So a plane distribution transverse to the fiber, any such choice of connection is going to give me a transitive lifting function, a way to lift the loops on the base to paths in the total space. And what I said earlier, that transitive lifting functions are unique up to homotopy, is reflected in this language of smooth vibrations in the fact that any two connections are homotopic. Anyway, so in the end, once I have a vibration and I choose such a lifting function, I get a module structure on the chains on the fiber over the chains on the base loop space. So here's the simplest non-trivial example, the Hopf vibration. So the base is S2, the total space is S3, and the fiber is S1. So any loop, so I've drawn here in the picture a family of base loops. Yeah, so the the base point is here, the very bright point. Yeah? And each such loop, yeah, if I apply it to a fixed point in the fiber, will give me some point in the fiber. And when I traverse a full circle of such loops, what I see in the fiber is that I go once around. Yeah, that's the hologram. Yeah. This is an example of a chain on the base loops of S2. It's a one chain that acts very non-trivially on the fiber. Yeah. If I want to express it at the level of homology, right, the homology of S1 is generated by a point and then S1. This is the computation that I marked in red here. And if I call X, capital X, this one chain on the base loop space of S2, it will act on the point by sending it to the fundamental class of the fiber, yeah? Which expresses exactly the fact that as I traverse this chain, I go once around the fiber. And this going once around the fiber exactly expresses the fact that the Euler class of the Hopf vibration is 1. And of course, the class of a point in the base loop space will act trivially, and that's always the case. And this is this is a consequence of the fact that I have a module structure of the DGA, and the class of a point is the unit in the algebra given by the homology of the base loop space, and the rest of the operations are 0 for degree reasons in this particular case. So this, the construction that I'm going to present, the Morse homology with differential graded coefficients, actually has an ancestor. And this is Brown's twisted tensor product. So Brown asks in 59, so you must imagine that it's just a few years, right, after Serre's thesis, right? The following question: is it possible to give a model for the chains on the total space of a vibration as being the tensor product of the chains on the fiber and the chains on the base, but endowed with a twisted differential? So what does twisted mean? It means that I look at the tensor differential and then I perturb it. Yeah? And this perturbing of the tensor differential is an algebraic manifestation of the fact that the vibration is locally trivial. And the answer that is given by Brown is yes. And in order to give such a model, yeah, in order to describe this perturbation of the differential, we need two ingredients. Yeah? The first one is the one that I explained, namely a module structure on the chains on the fiber. And the second ingredient is what is now known as Brown's universal twisting cocycle. And it's a map that's universal, which has degree -1 and goes from the chains on the space to the chains on the base loop space. Yeah. Morally, like if I have a dimension k family of points, yeah, or a simplex of dimension k, it's possible to turn that into a k-1 family of paths. Yeah. So I will not dwell on this. I think it's important to be aware of the fact that there is this ancestor, yeah, and we'll argue that the Barraud-Cornea construction is an analog of that in the context of Morse theory. So for Morse theory, we start with a manifold, we start with a Morse function, we pick a Morse-male negative gradient-like vector field, and we consider the compactified moduli spaces of Morse trajectories. So these are oriented as soon as I pick orientations of the n-stable manifolds. Yeah. They are oriented, and they are actually manifolds with boundary with corners. We have a choice, like as of today, we have a choice as to how fine the description of the manifold structure of the boundary is. But in any case, the boundary is described as a union, which is not disjoint, of products of similar objects. The reason why there's only a twofold product is that inside M bar, there's an arbitrary number of breakings of Morse trajectories. So we cover everything. There's some overlap. Triple products belong to intersections and so on. And the meaning of the sign here is that the product of orientation differs from the boundary orientation by this sign. So that's the data that we start with. And the construction of Barraud and Cornea is the following. They pick a coherent system of chain representatives of the fundamental classes REL boundary for all the compactified moduli spaces. So coherent system, meaning that, of course, I can pick for each specific moduli space a representative of its fundamental class, but we pick them inductively so that the previous equation, which is a description of the boundary of the compactified moduli spaces in terms of products of such, turns into an algebraic relation, meaning that the boundary of each such representative is expressed as a product of the previous one with the same sign. And now comes, so up to now, everything happened on the moduli spaces. Yeah? But now these moduli spaces are naturally of a geometric nature, and they evaluate into path spaces. Each gradient trajectory, as I drew it here, although it's, as it comes as a gradient trajectory, it's parametrized by R, it is also naturally parametrized by a finite interval, namely by the level sets of the function. So each moduli space evaluates into a space of Moore paths connecting two critical points. And if I push via this evaluation map, the previous representatives of fundamental classes turn into chains on these path spaces, which satisfy this relation, where now the nice thing is that what was previously a product becomes a concatenation, simply because one path followed by another path turns into, via this evaluation map, into their concatenation. And we know very well that if I fix the endpoints, the space of paths between two fixed endpoints is homotopy equivalent, actually homeomorphic to the base loop space. Yeah? So we can further turn this collection into a collection on chains on the base loop space. Yeah? And this collection of chains satisfies the same equation, where now we have, again, concatenation, which is the product structure on base loops. And in practice, if we want to turn those paths into base loops, it's enough to just pick, and this is what we do, we pick a tree that runs, I constantly keep erasing, runs from the base point to the various critical points. And if we collapse that tree, any path becomes a loop. So this collection I call the Barraud-Cornea universal twisting cosine. And the Morse complex with coefficients in a differential graded local system is obtained by just taking the tensor product. So here we think over Z or over whatever our favorite ground ring is, with a free abelian group generated by the critical points. And the differential is perturbed. And it's perturbed by taking a coefficient, applying to it the differential from the chain complex F, and on the other hand, using the universal twisting cocycle in order to twist that. And if you think of the previous picture in terms of vibration, it's really like every such element, mxy, represents a chain on the base loop. And this part of the differential will take into account how does that cycle, alpha, that we have to think of as living in the fiber, how does it spread in the total space, right? That's what it's doing. So since there were 3 or 4 slides, let me make the summary of the construction. I started from the compactified moduli spaces. I picked representatives of fundamental classes. I evaluate into path or loop spaces in order to obtain this collection, which I called universal twisting cocycle. And I use this collection together with the data of my module over the chains on the base loops in order to build a complex. And these 2 objects are analogous to what I had mentioned before in the Brown construction. So there's the chains on the fiber for a fibration, and then there's this universal object that's only defined in terms of the base. It does not involve any other data of a fibration, or it's just universal. It is defined in terms of the base. And theorem, which was proved by François Charette over Z-mod 2, and we reprove it also with arbitrary coefficients, that if we have a fibration and we take as local system the chains on the fiber with its corresponding module structure given by the lifting function, the homology of this complex is the homology of the total space. So this is the Morse counterpart of Brown's theorem.
And here the right-hand side is with coefficients in
No,
Z? Or...
this is Z, yeah. Of course, I mean, I could also put further coefficients on E as well, and that would amount to tensor whatever I have on X by something else, but yeah, indeed. So bottom line is that the Barraud-Cornea cocycle is the Morse counterpart of the Brown cocycle, and both of them can actually be described as a DG Tor, meaning I have a module over, not over a ring, but over a DGA, or differential graded algebra, which is these chains. And I'm computing a Tor group with Z. And what does this mean? It means that I need to find a resolution as a free module of using free modules over this DGA of Z considered as a trivial module. And indeed, hidden in the construction is such a resolution. So this would be a third point of view on the same construction. They can be understood algebraically as a Tor over a DGA. So yes, this is this is the end of the second part. And before I go to the Floer story, maybe you have questions about the Morse part.
Can you maybe repeat how you go from SXY to MXY, please?
By just evaluating.
Because this, okay.
These MXYs just evaluate into paths.
Okay, so these are paths. But...
Correct. What I denote by this P, it's genuinely paths. And I make this little distinction because the MXY is just the moduli space is there somehow before, and I make the distinction between the moduli space and then its image somehow in the manifold.
Yes, but then you go to omega of X, no? You
Yes.
replace
Then I
path.
go to omega.
And how is that done?
Well,
By choosing a path from each X,
There's
Y,
a-
and so on?
yes, there's this tree. Yeah. And
Okay,
so
that's what,
I choose a tree
okay, that's what okay, sorry.
inside X.
Okay,
And I can certainly go from
no, of course, it's clear. Okay,
Yeah.
I wasn't connecting the,
from the paths, I can go to based loops on
okay.
X mod the tree, and this is the same as based loops on X.
Okay, no, I understand. Okay.
Yeah.
Thanks, sorry.
No. Any other questions? So I'll get to Hamiltonian Floer homology, and somehow once we saw the story on the Morse side, we know what happens on the Floer side. And it's really meaningful to say now that, so I'll place myself in a symplectically aspherical manifold, I pick a Hamiltonian, and I want to look at Morse theory for the action functional defined on X being the free loop space of the symplectic manifold. Yeah? So the digilocal system now is going to be a module over chains on the base loops of X, meaning this, chains over base loops on the free loops of W. That's the natural notion in this context. Yeah? And let's say we work component-wise, and subsequently I will work on the component of contractible loops. Yeah. So it looks maybe weird to see all these symbols one after the other, yeah, chains on base loops, on free loops, but it's just natural. This is how it comes to us, and the procedure is the same. I look at the compactified moduli spaces of Floer trajectories. I pick representatives of the fundamental classes. I evaluate these into paths or loops in this space X, where everything happens. And so I end up with chains on base loops, on free loops. And once I have a module, I build the Floer complex. And we have to think of this as being Floer theory with coefficients in a fibration. So again, if I were to draw this, like I interpret literally a Floer cylinder in this context as being a path of loops. And that's why everything happens in here. Here's two computations. Yeah. First is a differential graded PSS isomorphism. Okay. So if I look at a closed symplectically aspherical manifold, if I pick a fibration and I look at the local system given by chains on the fiber, what I get is the homology of the manifold, as written here, with coefficients in the pullback by the inclusion of their local system, which is the same as the homology of the restriction of that fibration to the constant loops. Yeah. So only the constants matter, for the same reason why only the constants matter in in the usual first setting. Yeah. So that's one. Note that, of course, the PSS isomorphism we can write in full generality, say, I don't know, for a monotone symplectic manifold. Yeah. I do not really know, and we do not know, how this construction goes on when we have holomorphic spheres. Yeah. So everything that I'm doing here is specific to the symplectically aspherical case. So I call this PSS isomorphism, but I place myself in a setup where there's no holomorphic spheres. Yeah. So I think there's a very interesting story when there are holomorphic spheres, but it's not about that today.
So just a remark, Alex.
Yes.
With Jean-François, we looked a little bit what's happening when you have holomorphic spheres. And the first thing that happens is that this square in this complex is not zero anymore. Yeah. And which one can expect, but you know, it's not so obvious in advance because these are codimension 2 bubbling. So, and okay, and so we interpreted this square a little bit at some moment. So it has to do with some Gromov-Witten invariance. But
yeah, my hope is actually that even in the monotone case, somehow the construction can be modified by taking into account suitable Gromov-Witten invariance, so that D squared becomes zero.
So it's an interesting. So I think it's an interesting problem. The other remark is that this whole story that is 20 years old. So it's a nice birthday that you are providing to the, you know, with your new results. It's good for the problem is happy, you know. So
yeah, I think so. I think so. Yeah.
Yeah.
I mean, I am happy anyway. So.
Yeah.
So let me go to the second computation. And this is the differential graded Viterbo isomorphism. Now, I look at a closed manifold. I look at the fibration over the free loop space. Yeah. And symplectic homology of the cotangent bundle with coefficients in the corresponding local system is the same as the homology of the free loop space with coefficients in that local system. So there's a little twist coming from the usual story. There's spin and orientation discrepancy between symplectic homology and homology of the free loop space, but I'm not going to dwell on that. Yeah. So that means that if we look at suitable fibrations over the free loop space, yeah, we can compute symplectic homology of the cotangent model. Okay. And now I get to the proof of theorem 1. So I recall the statement, and I will focus on the statement when the degree is plus or minus 1. Yeah. So I take a closed oriented manifold, dimension n, which is not a k pi 1. And we're saying that contractible almost existent holds for any hypersurface that encloses the image of a closed oriented n-dimensional manifold S by a map whose degree is plus or minus 1. That's what we're saying. So I drew here a little picture. Yeah. So the image can be complicated. I don't know. It can have self-intersections and so on, you know, but it must have degree 1 when I go to the cotangent bundle and then to the manifold. Okay. So that's the statement. And the proof, I'm waiting for the slide to change, is that we consider on the free loop space the mother of all fibrations, the universal vibration, which is the strongest. That's the path loop vibration whose total space is contracted. So I denote it by this letter P star, else 0Q. Yeah, so I work only over contractible loops. And the image on the right is supposed to represent an element. Yeah, it's a path of loops that starts at the base point, which I consider to be a constant, and which ends anywhere. And the fibration is by evaluation at the end point. And the fiber is base loops on free loops. So what's happening when I restrict to the constant? Well, this cone here on the right needs to close up, and I end up with a sphere. Yeah. So the total space of the restriction of that vibration to the constant is actually an iterated base loops, is omega 2 of Q, or equivalently maps from S2 to the manifold Q that preserve a base point. Yeah, same thing. So that's the picture. These are the local systems. So the local system is going to be this guy, chains on base loops on free loops, as a module over itself. This is what the transitive lifting function does for the universal vibration. Yeah, it's tautological. The vibration is very strong, it's a universal one, but the module structure is very simple. And now we look at our tag. Yeah. So, sorry, it's a bit heavy slide, so I'm trying to I'll go slowly over it. Yeah. What on the first line, so we see as before. Sorry, again I'm symplectic homology on the upper right corner. Its classical part, which is the homology of the constant loops, and then the homology of the domain bounded by the hypersurface, right? And remember that we wanted to find a class here that would go to 0 and that would stay non-zero here. That's what we wanted. That's what we wanted. Because the image of that class would then have to be killed by a periodic orbit on the boundary of U. Yeah. So let's see. I'm saying that this map on the top, the horizontal map, is not injective if Q is not a K pi 1. So why is that? Because I can compute. Yeah. So on the right-hand side, symplectic homology is homology of the free loop space with coefficients, and hence homology of the total space of this vibration, and hence the homology of a point. So I still remember the moment when we realized that we were quite happy because the homology of the free loop space became suddenly very small. And that was very good. And on the other hand, if Q is not a K pi 1, the term on the upper left corner has homology richer than that of the point. In fact, we have equivalence between having the homology of a point and being a K pi 1. So that's where our assumption comes from. So under our assumption, this map is not injective. And on the other hand, this other map, the vertical one, is always injective because of our assumption of degree plus minus 1. Yeah. And we can see that on the diagram that comes right after. Yeah, so I drew it a bit differently. It's about a miraculous property of Schrick maps. Yeah, so if I have Schrick maps between manifolds of the same dimension, there's this wonder here, it's Q and S. There's this wonderful property that direct map composed with Schrick map is D times the identity, where D is the degree. And this happens with differential graded coefficients as well. And we proved it. So yeah, when the degree is plus or minus 1, this ensures that the Schrick map is injective. And when the degree is not equal to 1, well, it has to do with torsion. And that's why the assumption about rational being or not a rational k by 1 came about in the second item in theorem 1. So yeah, I think this is the proof. In summary, these Morse and Floer homologies with differential graded coefficients capture higher dimensional twists as those that happen in vibrations. And the fibers of those vibrations can be infinite dimensional, and in our application, they actually are actually infinite dimensional fibers of this kind are the strongest. These Morse and Floer homologies with DG coefficients behave just like the usual ones. They are filtered. I did not insist much on the filtered aspect. And there's a full package with differential, with continuation maps and homotopies. Yeah. And they lie in between homology and homotopy. Yeah. So they capture strictly more information than homology, less than homotopy, but then there's a balance related to the last item, which is computability. Yeah. So everything homological is more computable. So they may be useful for precisely that reason. And I think I am done. I thank you, and end with this little drawing, recapping the Hopf vibration, for which we know, I don't know, maybe we're used to think of it in many ways, like the pictures on the right, but the one that I'm suggesting today, thinking in terms of the holonomy of the vibration, is yet another one, which I think kind of encapsulates, captures the spirit of what I wanted to convey. Yeah. I'm done.
Thank you, Alex. Any questions?
Yes, I have a question, Alex.
Yeah.
As you know, if you want to prove the Weinstein conjecture on cotangent bundle, at least the simply connected one, you use equivariant Floer homology.
Yes.
So sort of my immediate reaction was, can you combine what you did with the equivariant picture and get something which
Yes,
is
agree.
even more powerful than both tools, I guess.
This is something that we want to do. We did not do it yet. Actually, I mean, there are the main reason is the following, that you know, very easily we must step outside from the world of a strict module over that DGA into the world of a infinity module. Yeah. So I don't think there's a conceptual, I mean, it's more of a technical difficulty. Yeah. So together with Mihai, we jointly supervise Robin Rigel. So he is giving a description of the Chas-Sullivan product in string topology using this language. And immediately there, he needed to consider A infinity modules. And when considering actions, the local coefficients need to be compatible with this action. So everything needs to act all along. And then on top of that, we need to consider a kind of homotopy action of the circle. So there's a number of intricacies related to infinity that we would like to understand, but we did not yet. So I'm totally in favor of combining the two. Yeah.
But can't you have just an S1 equivalent setting before putting the A infinity structure somehow? Or you need you seem to say that you need the A infinity structure to construct.
I think the action of the circle may be in this situation itself infinity type, you know, like what's an action of the circle in the algebraic world, and it needs to act on the coefficients. Otherwise, I don't know how to implement it. Yeah, and so I need an action of the circle in the algebraic world, and that would mean not just an action of z of x mod x squared. Yeah, it actually it has higher order operations, and I don't know yet exactly how to encode that. But it's certainly something that needs to be explored and that we would like to do.
So one way maybe is to think about finite groups that approximate the circle, and try to maybe use an action of some, a z mod p for p very big, that kind of makes it more discrete. But it's just a remark,
That's a good point. Yeah.
It's a bit funny because it's related to some approximability questions that kind of show up in any case. Another question I had, you mentioned that you have this spectral, not spectral, but filtered version, which is very natural, of course, in this. And one question we had for a long time about this, but it wasn't really looked at very carefully, is whether spectral invariance with these coefficients bring something new or not. I remember at some moment around 2010, we were hoping that yes, but then it wasn't so clear anymore. But now you have all this machinery going, so maybe you can, figure it out. So,
I mean, one thing that we used, we did use the first most rudimentary of spectral invariance in this paper, because we can also prove finiteness of the Hofer-Zende capacity for certain cotangent bundles with different coefficients. Yeah, so we do use some spectral invariant, and so it I don't know what to say. It does bring something new in the sense that it functions as before, but in situations that were not covered previously. So,
right. No, definitely.
In the way the spectral invariant will function as one would think of.
Right. But you see, the things that, as far as I know, wasn't clear to us, to me in any case, was that if you have the pi1 action showing up, which you have in your situation, then spectral invariance can be very different, taking into account various actions and things. But just from these higher dimensional moduli spaces, like when a manifold is simply connected, or you don't have any particular, pi1 showing up, at least we couldn't see what spectral, that the spectral invariants are more refined, or kind of giving better results than the usual ones. But it's just a question. I just don't know.
I think if I have to add something, it's related to maybe Jean asked a bit earlier, to the existence of product structures. I think then the next step that has to be exploited is existence of product structure.
So Charette worked on this somehow, but it's more complicated, this part. Yeah, there are different complications. Yeah.
May I ask you, so what happens in K-pi1 case?
Honestly, I don't know. Leonid. For example, I do not know what's happening for the cotangent bundle of a genus 2 surface. I don't know. I don't know. For
Well,
example,
what-
I don't know if the cotangent bundle of a genus 2 surface has. I was going to say if it has finite Hopper-Center capacity, but this we yeah. Actually, I don't know. Yes, I don't know that.
It's amazing. Yeah.
So what I can say is that the algebraic thing will only depend on what's called the unipotent completion of the group. Whatever. Now I even forgot what it is exactly, but there's some algebraic definition. But otherwise, indeed, I don't know any sort of general mechanism that would work for K pi 1. On the other hand, it's a little bit strange because you could say, okay, take a hypersurface in a cotangent of K pi 1. Either it surrounds the zero section, at least topologically, and then you can apply Hofer and my result, and you get periodic orbits, or it doesn't, and then morally it should be in the cotangent bundle of something smaller, and then it should also work. Of course, that's not correct. I mean, of course, that's not correct, but it would be really interesting if someone found a counterexample to counter this intuition.
I agree.
Sorry, maybe I didn't understand something well, but if we take this cotangent bundle of a genus 2 surface, which corresponds to hyperbolic metric, this does not have any contractible orbits, right? So
no,
no.
So
no, but I mean, yeah, it does not have any contractible orbits, but it has many non-contractible ones.
Yes. So I thought that Leonid's question was: is there some hope to obtain some similar result as to K pi 1? So
I think the Euclidean metric on the torus kind of.
Yeah.
No.
Yeah. That's even simpler.
Non-contractible. Maybe simply interesting. So, what is the right structure which you should consider?
Yeah.
Maybe you can modify this construction. Whatever. So
somehow the way I see it is that for non-K pi 1s, we may hope to prove that there's always a contractible close characteristic, and for K pi 1s, we may hope to prove that there's always a close characteristic without contractibility assumption. That's how. So the fact that we have some result that holds for non-K pi 1s, I think is good. I mean, it shows that we're on the right track, because I don't know how all manifolds that are K pi 1s look like, but all that I know of, which are those which have metrics with curvature, with non-positive curvature, all those don't have contractible geodesics. So from a topological point of view, being somehow putting the frontier at K pi 1 is good. Yeah, but I don't know what happened there.
So is there any chance for global to global principle like in Barraud-Cornea story? So you want to get Meyer Vitoris for Poisson commuting subset, so to say.
Well, my first reaction would be yes, because although I described that these DG local coefficients as being modules over chains on the based loops, they have a sheaf nature because they come from vibrations. So we could I think there are some natural maps that one could use. So for example, one equivalent description of such a local system would be not a module over chains on the base loops, but rather a module over chains on the path category, right? I take the category with objects, all the points on the manifold, and then morphisms, the chains on the paths that connect these points. And now to each open set, there's associated such a path category of the paths that stay inside. And then there are inclusions. So maybe one can extract something from that structure in the spirit of Barraud-Cornea.
There is certainly a Meyer-Vietoris sequence in this framework, which is implemented like in the usual Morse setting.
It must, I mean, it's certainly the case when it comes from a vibration, and then in general, right now I don't. But you're certainly right. Right now I don't see it, but in full generality, it's certainly the case from a vibration. But okay. Indeed, you need to start with a local system over the union of the two open sets or whatever, the thing on which you want to compute. And then you have restriction maps of that local system over the intersections and over each open set. And using those, you obtain the Meyer-Vietoris sequence. Right. So that actually, you are totally right, Mihai. And that actually comforts me in what I answered to you, Leonid, because it's of the same nature, this restriction. Yes.
Okay, so if there is no further questions, let's thanks Alex again.